Brian, if you want, come up here and sit. So good afternoon, and I'm Ben Hill with Georgia Tech's Venture Lab program, and I'd like to welcome you to today's Clean Energy Speaker Series, where, of course, we're talking about nuclear power. Um, today's program is part of an ongoing discussion about the needs and opportunities for clean energy and clean technology in meeting energy demand in the Southeast for the next 20 years. So for the last couple of months, we've looked at natural gas. Today we're looking at nuclear, and beginning the next semester or the next term in January, and I think January 25th to be exact, we're going to turn the discussion on clean energy and clean technology into a discussion on economic development and considerations of both established and new ventures in the clean energy, clean technology area. So be sure to mark your calendars for the last Wednesday of January, where the topic will be state and local impact of clean energy and clean technology. Um, a number of individuals and organizations make the Georgia Tech Clean Energy Speaker Series possible, and I'd like to recognize and thank them for their ongoing support. We have a number of advisors to the series. I think ranging from Jay Hakes at the Carter Center, Marilyn Brown, Valerie Thomas at Georgia Tech, Deepak Devan, and David Scholl, also at Georgia Tech, and then Ken Ostrowski with McKinsey and Company, who provide great advice and direction for this program series. We also have had ongoing support from the law firm Sutherland. We thank them. McKinsey is a thought partner in this adventure. And then we've also had support from not only Georgia Tech's Venture Lab and Enterprise Innovation Institute, but the South Base Institute, as well as other organizations on Georgia Tech campus, the Brooke Byers Center for Sustainability, the Strategic Energy Institute, and the Georgia Tech Office of Sustainability. So, you know, the old saying, it takes a village to make some things happen, and we appreciate the ongoing support of all these different groups and individuals. Today's presentation and previous presentations can be found on our website, which is secleanenergy.gotech.edu, and you'll see the video webcast as well as archived PowerPoint presentations on that site. Kind of the format of today's program is introductions by Dorothy, and our speakers will make their presentations, and then we'll have a Q&A session. The microphones will be passed around during the Q&A session. So for those of you here, please be sure to speak into the microphone so our participants on the webcast can hear your questions. For those of you participating over the web who might have questions, I would ask that you send an email to me, and I will pass those questions on. And my email address is ben.hill@georgiatech.edu. ben.hill@gotech.edu. And also, as we pass the microphone around, if should you have any comments or would like to make any comments, in addition to asking questions, I would just ask that you kind of keep your comments brief, so everyone will have an opportunity to participate. Let's see. So at this point in time, I'd like to introduce Dorothy Franzoni, who's a partner at Sutherland and is in chair of Sutherland's Renewable and Alternative Energy Practice, who will introduce our speaker. Dorothy.
Thank you, Ben. As Ben said, I'm Dorothy Franzoni. I'm a partner in the Atlanta office of Sutherland, Asbill, and Brennan. We've branded ourselves Sutherland, you know, like Coke, but we're still Sutherland, Asbill, and Brennan. And I'm the chair of our Renewable and Alternative Energy Practice. And it's been our pleasure to be a sponsor of this speaker series now coming on 2 years. And we've had a terrific slate of speakers up to now, and we have a really terrific slate today. So I want to briefly introduce each of them. They each are very much experts in their fields, And I don't want to take up time introducing them too long, but want to give you a flavor of who we have with us today. Glenn Shadeen is a professor here now at Georgia Tech. He came to Tech in November of 2010 from the University of Florida in Gainesville. His experience includes a good bit of time in the Air Force with the Air Force Technical Applications Center and work with nuclear, biological, and chemical arms control and advanced technology defense programs for the U.S. government. He's also served as a technical expert and research lead for critical reviews supporting the Limited Test Ban Treaty, the Intermediate Range Nuclear Forces Treaty, and numerous classified defense projects, which I expect he will not be telling us about today. But what he will be talking with us about today is the current state of technology in nuclear fission. Glenn has a Bachelor of Science from Texas A&M University, a Master's in Science from the Air Force Institute of Technology, and a PhD from the Pennsylvania State University. Our second speaker is Howard Axelrod, who is an economist and has more than 40 years of experience in the utility business working with electric and gas utilities. He has testified before numerous state regulatory agencies and the Federal Energy Regulatory Commission on topics including resource planning, power contract management, and utility operations and management. He's worked for GE, several state of New York agencies, including the New York Public Service Commission and the Resource Management, now known as Navigant Consulting. His clients include Southern Company and Georgia Power, Energy Authority, Santee Cooper, Mirant, Brookhaven National Laboratory, and many others. Howard will be talking with us today about the economics of nuclear power in today's world and beyond. He has a PhD in managerial economics from Rensselaer Polytechnic Institute, an MBA in marketing from the State University of New York, and BSEE and MSEE degrees in power systems from Northeastern University. And finally, the third panelist today is Brian Debs, who comes to us today from the Lawrence Livermore National Laboratory. Brian has 38-year career in the nuclear power industry, and currently is sharing time in his life between living here in Georgia and out on the West Coast. He served in the Navy as a commissioned officer and then joined Westinghouse Electric as an operations manager in support of their nuclear propulsion program, and later was a member of the U.S. Nuclear Regulatory Commission's management team. He has held executive positions with Gilbert Commonwealth Corporation, an architectural and engineering firm, and Ontario Power Generation Company in the management of 20 nuclear reactors and heavy water production and tritium recovery facilities. Ryan's going to be talking with us today about the future of nuclear, including nuclear fusion. He's participated actively in the World Association of Nuclear Operators International Advisory Council and has served as a director of several corporations and chairman of the RO International Institute. Brian has a Bachelor of Science degree in mathematics from Purdue University. So with that, I'd like to introduce our first speaker, ask Glenn Shadeen to come up and give the first presentation.
Well, thank you very much for the kind introduction. It's probably not evident to you, but I spend about half of my time doing nuclear power, nuclear energy, nuclear power related research, and the other half of my time I do what would be loosely coined as defense program research. So still doing various projects for the government and the power industry. And interesting time, just as an anecdotal thing, I spent a month in France working with EDF, the Electricity de France. My French is getting a little better after spending that time there. Working with their engineers on advanced code development for full core simulation, hyper-accurate simulation of neutronics in their cores. And I wrote a code that they're using now to benchmark And so it's been kind of exciting to do that with them. But you see a real flavor for nuclear energy in France. I got a really up close and personal way to relate to how the French run their nuclear program, and it's basically they just say this is the way we do it. We will have nuclear. We're going to have nuclear now and in the future, and this is how it's done. So it's kind of nice to go to that environment, because certainly there was a lot that happened in this last year with regard to nuclear energy, particularly Fukushima and the issues that surrounded that event. I was involved in that quite a bit in trying to give assessments to CNN, or reality checks, I would say, to CNN and others who pinged us for technical expertise on what is exactly happening at what time. But I wanted to give a very brief overview of our one slide just to talk about our Georgia Tech nuclear and radiological engineering program, medical physics program. And I want to jump quickly into the Fukushima Daiichi accident, give a quick overview, and talk about chain of events and how that moved to shape some of the opinions that we're seeing today. Oh. Then I'll talk a little bit about the nuclear option and where to go from here, and to give you a perspective on a study that was done called The True Cost of Energy, where it looked at the actual cost of energy and the long-term needs. So at Georgia Tech, we have close to 300 undergraduate and graduate students. It's a very robust program. We have a lot of really expert faculty. I'm really pleased to be part of the team here at Georgia Tech. It's been over a year since I've been here, and it's been an outstanding year for me. I really enjoyed being here. We also held a sustainable nuclear fuel symposium in this past year, which we had folks from industry, government, and numerous organizations participate in that to look at sustainability of the nuclear fuel cycle as it's currently done in the United States, or currently not done, depending on your perspective of how that is handled. Anyway, it was a very successful conference, and there's a website on this symposium for sustainable nuclear fuel management, and the talks and various things are available, and it's a nice online resource. You may want to check that out. But it was a very well-attended meeting, and we had some very, very interesting keynote speakers for that. Of course, launching back into March 2011 of this year, you had a really perfect storm of events, of an earthquake, resulting tsunami, and then therefore a nuclear disaster. Station blackout became a term that most people suddenly became aware of. This facility at Fukushima Daiichi was designed for a 6-meter tsunami. The actual height was more than 8 meters. Basically, it wiped out their auxiliary cooling. This is an issue with the older plants. They don't set up convection cooling. The new designs do, and I'll comment more on that. And the Fukushima Daiichi plant, about 10 kilometers away, was upgraded, and they built their system several meters higher than at Daiichi to mitigate this potential, even though it was considered remote, for a very tall tsunami. So you didn't hear anything about really Fukushima Daiichi, which is, again, just down the road, because the Daiichi plant was actually nearing its scheduled retirement phase, and it was viewed at the time that they didn't want to upgrade because it was supposed to be such a remote event that, they didn't think they would need it. Obviously, hindsight is 20/20. And it's easy to armchair this, but in any case, this perfect storm of events led to some catastrophic failures in the reactor systems. And the other, I put this slide in to not really launch into a technical discussion on GE BWR Mark 1 containment, but basically we're storing our fuel in the spent fuel pool at the top of the plant. It makes it easy because you take the cover off, the head cover off the vessel, and it makes it easy to get to. It also causes real problems if you're not able to dump your waste heat out of the building, as happened. So we had a problem with elevated temperatures in spent fuel pools, and these spent fuel pools are not in a pressure boundary like they are in the core. So a lot of questions have now been generated about the status of these particular plants and how they're designed. The good news is the plants are pretty robust. The bad news is they did have failures and they did have issues. And the other thing is that these plants are fairly old, and there are not that many of them out there at this time. A lot of them have been closed, but they still do exist, and they are nearing their end of life. And there's probably more to come from the NRC. The NRC has been pretty much swamped since March to reformulate and reevaluate and look over a new policy on how these plants are managed. So the lack of active pumping led the nuclear fuel to be uncovered. You have this problem because we like to use zirconium in our fuel rods because, well, the zirconium doesn't absorb a lot of neutrons, and it's a really good metal for containing that nuclear fuel. It's the primary, basically, pressure boundary for. We do have fission gases that are produced. I'm not sure if a lot of people realize there are gases that are produced that are radioactive, and they're contained in that fuel rod. And the physics of the plant designs are such that zirconium and zircaloy, the alloy, makes it a very nice material, except when you get to around 2200 Fahrenheit and then you start having a zirconium water reaction and release hydrogen gas, which when combined with oxygen, well, we all saw the Hindenburg, right? And that caused a lot of problems. And it's very disconcerting for people to see a nuclear power plant and suddenly a big explosion occurs and blows all the panels off, and people, naturally, the nuclear engineers said, well, the pressure vessel wasn't hurt by that, it just blew out the panels. But most average folks who don't really consider this too much, you see a building blowing apart, well, you get concerned, and so this is an issue. So we're looking at, the other thing about fuel design is how can we redesign the fuel to avoid this kind of scenario? Are there other alternative materials we can use to do the job of the zirconium cladding? But the problem you have right now is not so much solving the material problem, it's making sure that the reactor is designed in a manner to where if you set up natural convection cooling, you don't have to enter into this because the temperatures never do get that high. In this case, it did due to the, again, calamity of events that occurred. The other issue is this event and all the subsequent events going on in Japan gave pause to folks who are in charge of spent fuel in the United States, where we have probably 5-6 cores worth of nuclear fuel racked in our spent fuel ponds, basically because the government has failed to identify a waste policy where the utility can send that fuel for ultimate high-level waste processing and or disposal. So it caused folks to actually rethink this and say, okay, we really do need a better policy on this. One thing I thought I'd clarify, just because there's a lot of discussion about decay heat and decay heat removal and what is this. When you shut a reactor down, I have a metric here, just if you've been running your reactor for about an infinite amount of time. This assumes a long operation, so near infinite time. When you shut the reactor down, 4.7% of the reactor power is still coming out 10 seconds after you shut off the reactor as decay heat and delayed neutron effects and other things. And so even after 10 days, you see there I have 0.3% of the original power is coming out as decay heat. So the decay heat is an issue, and most fuel has to be cooled for several years after it comes out of the core if it's gone through what I would call an average burnup in doing its job. And you have to keep this cool. It will keep, there's no way to turn that heat source off. It's Mother Nature decaying chains of progeny of radionuclides that give off heat. So the key is, as I mentioned already, is to design your reactor so that your reactor, if you shut all the pumps off, you set up a convective cooling loop that basically can remove that heat and set up a heat sink. Now, that's not to say that if you set up natural convection, you're okay. You still have to have a way of removing heat, because physics is physics, heat is heat. You have to move it somewhere. And but most of the modern reactor designs have provisions for 1 or 2 or 3 days without taking any drastic action to cool the plant. Rather than in an hour, we're going to have to start pumping seawater because we have no other water source, which is what happened in Fukushima. So, potential role of nuclear power is an important one in our energy policy. And right after the Fukushima Daiichi accident, the CNN folks called me and asked me if I would write an op-ed piece. I don't know if you happen to see it. It's still out there on the web, and the title of that article is The Necessity for Nuclear Power. And I addressed a lot of the issues that I talk about today, but I also addressed several key points about nuclear energy and compared to fossil fuel energy. And there were several prominent quote-unquote founding fathers of the environmental movement that have endorsed nuclear and have since renewed their endorsement even in light of the Fukushima accidents. Nuclear power has to have a role in our sustainable energy development, but is it sustainable? Well, yes, it is if we make the right decisions regarding it, and there are several. It's a good solution overall for our energy needs. It has very high energy density. 50 years of nuclear waste operations you could take all that nuclear waste, they talk about mountains of nuclear waste, that would just fill one football field about 20 to 25 feet high for 50 years of high level waste. If we reprocess that waste, because 95% of the fuel is recyclable, you would get that high level waste volume down to 50 years just to the end zone of that football field. So it's an important issue because it's high energy density, and if you do it right and you don't use 40-year-old plants, which we've come a long way in 40, 50 years, I believe it's a smart way to go. Now, smart site location is important. I think it's probably a really good idea to not build these things on a fault line. That seems to be pretty common sense. Uranium and thorium resources are also sizable, on the order of 100 years. But clearly, and I'll be the first one to admit, the waste issue needs to be addressed. Now, what's interesting is Japan, Russia, France, UK, everybody has closed their fuel cycle in some manner by recycling their fuel, everyone except us. The latest folks to involve themselves in the recycling push are India, and they're an emerging nuclear power because they have a lot of power to provide. But we need to address the waste, because if you don't recycle, you start piling this stuff up. We have currently around 65,000 metric tons of waste. That's enough to where if we built a pilot plant, that pilot plant would be busy for about 30 years based on the current stockpile we have. So where from here? Now cleanup, spin back to, for a moment, cleanup of the Daiichi plant will be costly, and I've looked at some estimates, and it's around 10 years to clean that site up. It is a mess. You take 4 nuclear power plants and you really do a number on them, and that whole site is going to be a mess for about 10 years. Design of the backup generators is now under a lot more scrutiny by NRC, even for anything in the U.S., just because. And again, this emphasis on passively safe designs, as they're called, are now in the forefront. But energy use is growing by 19% in the next 25 years. We're going to be competing with, we're already seeing it, China, India, others, rapidly growing economies. So despite the hype and renewables, I really love renewables. I think they're great. But we do have to be realistic about renewables in that the current upper limit is that they could provide around 20% of our energy demand needs. So 20% is a small number. And if you're not going to burn oil or coal, you're going to need something that's not going to contribute greenhouse gases. And nuclear, therefore, must be a major component. But we need to take a hard look at making the fuel recyclable. And as I mentioned, I spent a pretty good time in France working with their French electric utility. And they have basically a complete and integrated nuclear power and fuel cycle. And it's just a matter of, if you talk to them, they just said, this is how we do it. 85% of their fuel is currently reprocessed. Now, let's say if you don't want to reprocess the fuel and you could talk folks into a repository. Let's say we're going to dump all the fuel into the repository and just keep it there after it's used once. You're going to need a new repository. One Yucca Mountain is not going to be enough. You're going to need several Yucca Mountains over a very short period of time. You see that in this graph. And the solution really is, the takeaway from this is you have to close the fuel cycle and recycle that fuel and recover that 95% that you can put back in the reactor. It makes no sense not to. A study was done by Externe, called Externe. It was performed by the European Commission, and it basically examined the cost, the true cost of energy, because for all the folks, I think coal is great too, but the problem with coal is, we talk about nuclear waste. The waste for coal, well, you're all breathing it, we're all eating it, and the government guidance on why you're not supposed to eat so many fish is because you have mercury in the fish, and some of that mercury comes from burning coal. So the waste is distributed across the landscape. Coal is coal. There is clean coal, but really, truly, there's no such thing as truly clean coal because you always have some emissions. So every energy source has an operational cost. You have to accept the risk and cost that comes from each energy source. But they did a study anyway with the European Commission and found that nuclear has significantly lower external costs relative to the other energy sources. And I reference this table. You can go look up the Externe study. So long-term needs and necessary actions are we need to reduce the U.S. backlog of waste. We need to try to avoid the change of direction every 4 years. It seems to correspond with the election cycle. And we do need a comprehensive strategy. And I participated in feedback to the President's Blue Ribbon Commission on energy and nuclear energy policy. And we gave many of these recommendations because they asked Georgia Tech for its feedback from academia. And actually, we're pretty familiar with the industrial needs in the nuclear industry. Long-term needs are the biggest. Long pole in the tent is not really technical. It's all political. We just have to make a decision. The other problem is 50% of all the nuclear professionals that currently support the current industry will retire in the next 10 years. Half of our workforce will be gone. Therefore, we need to really crank up our output of engineers and scientists who can manage even just the current resources without the current growth that we say we need. So, in conclusion, we need nuclear plants to take the place of future plants to provide non-fossil energy needs. We need to be smart about where we put them, no question. We need to use the passive safety design component. We need to close the fuel cycle. We need the government to step up and make that decision and firmly carry through with it. And lastly, we really are in critical need for nuclear education just to provide the nuclear professionals to even service the current industry because of the massive retirements that are going to be going on in the next 10 years. And that's part of the reason why I went to academia. I did retire from the Air Force. I was a lieutenant colonel in 2004. I retired. I am older than I look. But I went into academia to try to solve this problem of nuclear training because it's a big issue. So that's all I have to say. Thank you very much for your attention.
here, why don't we up, down. Well, thank you very much for being here today. And as a new resident of Atlanta, you'll catch when I say, need the mic? Okay. When I refer to my hometown as Albany, you know it's not Albany from Georgia, Albany, New York. So, but I do enjoy the opportunity to speak with you. And my approach is going to be a little different. I wasn't sure how to go forward with this. And actually, before I go on the slides, I'm going to do a little educational aspect to it. I do a lot of risk analysis for the energy industry. And I could say that I'm neither a opponent or a supporter in the public forum of nuclear power plants. I'm a supporter at times, and I'm not. My role is to advise my clients to understand the uncertainties and the business risks associated with any form of generation. And so currently I'm working on, for a client in Vermont, supporting the continued licensing of Vermont Yankee nuclear plant, which is reaching its retirement age. But on the other hand, many years ago, I was the lead economist on the Shoreham Commission, which led to Shoreham, New York, the nuclear plant that was completed but never operated. So I'm going to be talking about risk and uncertainty, but not risk and uncertainty as Glenn just talked about in terms of what would happen if, but more in terms of business risk and economic risk associated with making a decision to build a nuclear plant. And some of that falls into financial analysis, regulatory uncertainties, and so forth. And I'm going to try and keep it focused. A half hour or 20 minutes can never do this service, so I'm going to limit my discussion to a few issues, but give you a flavoring of the type of things we look at. One thing is that we're looking at, will the nuclear power industry in the United States survive the post-Fukushima events? And really I'd like to turn that around, because I think there's a more immediate issue, and that is, if you're from the perspective of a supporter of nuclear power in the United States, is can it survive the Marcellus shale oil or shale gas? Shale gas has emerged as we saw for many years before shale gas, our proven reserves were declining in the United States, such that the volumes of natural gas, we were talking about 20 years in the future. I mean, literally 20 years from now, we could be out of natural gas. And that number is now well over 100 years, depending on who you're talking about. And that's because of the technological advancements have been possible of extracting large volumes of natural gas reserves that we have in once areas that were very difficult to retrieve in an economic way. So we're going to talk about that, because that is a game changer. And that's really recent. Now, I've been in the business for a long time. And I'd have to say, I'm dealing with this topic every day. And if you asked me 5 years ago, did I ever hear of a Marcellus gas field, I would have said, I don't know what you're talking about. I just don't know what you're talking about. Or learning about the technology, because I'm not into mining or fuel extraction methodologies, but now all of a sudden a lot of us know about these methods and what they call fraction, and we're learning a bit also from layman's point of view that it has an environmental impact and environmental cost that hasn't been fully yet internalized. My mentor when I was younger and growing up was a fellow named Alfred Kahn at Cornell University. He was the chief economist under Jimmy Carter, and also deregulated the airline industry. And Fred just passed away, and I had a chance to interview him for the American Bar Association. Asked me to interview him and on whether or not he thought what happened in the airline industry was, good or bad. And I can't repeat what he said, but it's a military term. He said TS. So but in any case, he felt that competition held out the best. But in any case, let's go through the nuclear events, and it really doesn't matter to me what the cause is, whether it's the NRC responding to the new knowledge, the lessons learned from Japan, or whether or not it's the economic drivers that provide alternatives to other forms of generation. And so they both have an effect because, as we'll discuss in a couple of moments, is that there are key things. And I'll summarize. If you look at the three baseload forms of generation, we talked about renewables a little bit before. Renewables tend not to have the sustainability over time. Obviously, wind will operate when the wind is there to operate those power plants. That represents about 30% of the time. Solar, as you know, that solar, until we get effective storage capability, is only during the intermittent hours. Whereas baseload generation, like coal and nuclear and combined cycle gas turbines, can operate 24 hours a day, 365 days a year, and provide that base amount of electricity that we need constantly. And so we're going to talk about the two of the three. I chose not to talk about coal because I don't have enough time, but it has the same aura around it. It has its own unique strengths and weaknesses. Nuclear we're going to talk about is, as it whittles down to, is the capital cost. How much does it cost? The Shoreham plant that I referred to on Long Island originally was estimated to cost $250 million. It was over $5 billion by the time it got done. Now, half of it was caused by delays and the cost of interest incurred because of the construction delays. But other plants have risen that. The Vogtle 1 and 2 plant, which I was a consultant to Georgia Power on the need for power assessments before the Georgia Commission, Public Service Commission. Those plants were well into the $6 billion range. It's very capital intensive, so slight differences could mean a major effect in terms of the overall economics. Coal, on the other hand, we talked about, has incredible environmental and safety issues. There's more life lost on a coal plant than, I think, in probably a month or two than in terms of mining accidents and railway accidents and so forth than we have ever experienced in the United States on a nuclear plant. But the environmental impacts are significant, whether it's sulfur, carbon dioxide for global warming, nitric oxides, heavy metals, mercury, lead. These are all serious impacts. But on the other hand, we have more coal-related energy resources in the United States, and if you go over to Saudi Arabia, they have an oil. I mean, and it has no other uses, or few other uses. Coal can be used in some industrial applications, but it substantially has a usefulness of being burnt as a fuel. But the environmental impacts. But let me go through those in a second. What I'm going to try and do today as I go forward is just briefly go over some of those comparative uncertainties and how they affect. There's no question that nuclear power is important to this country in terms of a resource that we need for production of generation. Not only is it important for our growing demand and our environmental concerns, but it's also important that we have 104, 103 nuclear plants, most of them of a vintage that are at least 20 years old, if not many closing into their life of 40 to 50, maybe 60 years. So over the next dozen or 24 years, a lot of that generation is going to be retired. And so therefore, to replace it, we got to think about replacing it. I did a study for a business group in Westchester, New York, because in that time the leading candidate for president, Hillary Clinton, was opposed to the plan. And she lives in Westchester. The governor at the time, I'm embarrassed to say, but Eliot Spitzer was his short tenure in New York. He was opposed to the plant, and the county executive, and that's one of those cases that they not only didn't build it in the right place, we're talking 20 miles from New York City. I mean, in a 20-mile radius, you got probably 6 or 8 million people that would have to be evacuated should a catastrophic event. But on the other hand, your choices are limited. And of course, the environmentally focused people were saying we could put windmills. Well, 2,000 megawatts, which is the size of those two plants, would have to be replaced by 2,000 megawatts of wind. But really, a wind only runs a third of the time, so I need 3 times that. So I need 6,000 megawatts of wind, assuming I could distribute it a way that, a third of it was running now and a third is running. And a typical wind generator, those big generators, the wings of those things are, 100, 200 feet wide, yards? I mean, they're massive. Well, they're only between 1 and 1.5 megawatts, so we'd need 6,000 of those. Vermont is the same situation, and it's interesting in Vermont, those people said we want to have wind, and it turns out that in 20 years, wind in Vermont, which you would think with all the mountains that they have and the open spaces that they have to, they don't have a large population. They say there's more cows in Vermont than there are people. They went from 8 megawatts 20 years ago of wind to 8 megawatts today. So they haven't really moved very fast, and yet they'd have to put in the equivalent of maybe 600 or 800 of them to replace the power. But, so we get a lot of dialogue. I think the biggest risk in nuclear plants is combined cycle gas turbines. For a couple of reasons. They have a very low capital cost. A lot of the components of a combined cycle plant can be built in a factory setting. So the economies, it's like a mobile home versus building a custom house. A lot of the components can be driven up on flatbeds and assembled. So what we're talking about is a capital cost of probably less than a third of a nuclear plant. Whereas a nuclear plant today could be anywhere from $4,000, $5,000, $6,000 a kilowatt. A combined cycle is anywhere from $1,200 to $1,400. Pardon me? 1,000? Well, okay. Well, anyhow, I'm from the Northeast, so the costs are a little more expensive. It takes fewer years to construct. You can literally go from the planning stage right through the completion stage in a couple of years, whereas nuclear, between the regulatory process and the construction cycle, could be 8 years, maybe even 10 years. It has, while it does pollute, it has no sulfur emissions. It has some nitric oxide concerns, although those are local and those are controllable. And it has carbon dioxide emissions, but it's about 1/3 those that are produced at a conventional but highly efficient coal plant. So it's pretty low. It's not totally gone. There's no waste, no fly ash, bottom ash that comes out of the burning of a power and a coal plant. Our supply of fuels is substantially, when I say substantially, it's probably 90-some%, maybe 98%, except for some regions like in the Northeast, Boston area. The fuel is domestically produced as opposed to LNG, which is liquefied natural gas that's imported, but substantially natural gas. And with Marcellus not only being a vast quantities, it's located closer to the areas that need it most. So until the infrastructure is placed, it's a little easier to get to. It's a secure delivery. It's underground pipelines. And there's been minimum public opposition whenever it's sited in a location. It doesn't seem to be the same type of draw. So those are some of the things. It's highly reliable supply, and we talked about the Marcellus. While that has a big question mark on environmental costs, as I talked about a little later, we're talking about $2 to $3 an MCF, that's a million cubic feet, is what they're estimating is if it was going to cost to the true environmental externalities, if there is issues, which means today's price of $3.75 or $3.90, could be as high as $5 or so, maybe a little more. Relative to historically, pre-Marsalis, the prices were averaging well in the $8-9 range. And worst catastrophic event we knew of was when the Hurricane Katrina wiped out a major infrastructure with the natural gas distribution, and it rose to close to $14. But we're down at $3.50, $4 range, and we'll talk a little bit more on the economics of that. I just talked about it's difficult to project. I used in my little analysis that I'm going to do for you a doubling of price to $8, just to see what impacts. The other big uncertainty that we deal with, and it's kind of interesting, it's kind of a utility industry, electric industry, is our major lobbyists in this country. Southern Company is one of the most vocal and powerful companies in the country in terms of influencing Congress. They spend a lot of money, and they have a lot of assets at stake, and they got a lot of industry that supports them. But so does Entergy, or Exelon, I'm sorry, Exelon, which is Philadelphia Electric, Commonwealth Edison over in Chicago, and other utilities that they own, are on the opposite side of an issue we're dealing with on clean air relating to carbon emissions. Entergy and Exelon, they both are major owners of nuclear plants and would gain financially if there was a carbon tax or cap and trade type of protocol that priced out the value of carbon dioxide emissions. In other words, if you emit, you have a choice, either control it or pay for it. And so there's a group of utilities that tend to own nuclear plants that are in favor of stricter regulations because the value of their assets grows. And then there's a group of utilities like AEP and Southern Company that have a fair amount of coal, and they favor a more moderate or mitigated approach towards cap and trade. Well, that's a big issue. A coal plant, and I'm going to throw some numbers out at you, but it just works out nicely, that a coal plant has an efficiency, and we measure that in a heat rate of about 10,000 BTUs per kilowatt hour. You don't have to remember it, and it's not really a good cocktail party statistic. But that translates into, if you had a competitive market, it translates into about for every dollar of a carbon tax translates to $1 per megawatt hour of production costs. So a $20 tax, which they're talking about, would be $20 per megawatt hour for a coal plant. Well, in a market that's around $50, add 20, that's a lot of money. That's 40%. It drives the economics for a coal plant. So carbon issue is a big issue, and we want to take a look at, be careful. Now, with a combined cycle plant that I'm going to focus on as comparison, it's roughly 1/3, and it's still a big impact. So for every dollar, it's 30 cents or something like that on the production costs. Some of the things on nuclear, and since I'm comparing the two, I'm coming down a little heavier on them, but they've been wrong an awful lot of the time. I don't know of any nuclear plant that was built on time and under budget. Just don't. There's a lot of reasons. We learned a lot. It's an important technology that drives a lot of safety considerations. 3 Mile Island drove an awful lot of our redesign of our nuclear plants for emergency core cooling systems. So a lot of them had to be redesigned, just as we were building an awful lot of nuclear plants. There was a lot of chemistry knowledge we had to gain in terms of inner core stress corrosion, in which the heat and the radioactive effects were degrading the containment. We had to learn a lot about that. There was a lot of rationale for it, but the reality is that over time, they cost a lot more than we thought they would cost. The events in Japan add one more aspect that says we're not sure. We're not sure what the NRC is going to end up saying or doing, which might impact the ultimate cost. That's just one event. Then we had the earthquake outside in Virginia or Maryland area, which just as a point of reference, I just got a call this week. My skylights in my office, I have a home office in New York, the inner glass shattered and split from the earthquake. Now that was felt in Albany, New York. That was pretty heavy earthquake. We know that the design of the nuclear facilities in that area were not designed for that level, although they experience, doesn't mean that they experience minimal damage. But the fact of the matter is we're learning a lot of things. We have the events over in Japan. We have an earthquake on the East Coast that we never thought would be that large. How that influences the cost of building the plant, I don't know. But I don't think it's going to go down. I don't think these events are going to say, geez, we overbuilt and we can cut back. So I don't think so. Because of the capital intensity of nuclear plants, there is it costs a lot of money. The two Vogtle plants are going to be about $16 billion. And it doesn't take a financial analyst to realize that if you're costing you 5% interest a year, I'll give you a low number, it's a 5% interest on a multi-billion-dollar plant, that at the end of the project, if I have a 1-year delay, it could cost me, what's that? 1.6 billion. Well, fine, that's 10%. So it's about $800 million for a year delay, which is not uncommon. Get a several-year delay, and it could go up. If the company doesn't have the financial resources to maintain that level of payment, then their credit rating goes down and their interest rates go up, just like we do. We max our credit cards. So it's a cascading effect that we have to be careful with. All right, let me go quickly through some of the things I wanted to do. What I've done for my clients is I have a software program that looks at some 2,000 to 3,000 variables that go into nuclear, coal, combined cycle, clean coal, wood, and looks at the life cycle. It measures it in, for those who are familiar with it, it's primarily we look at net present value, levelized cost. Net present value is all of the costs that go into the design, the building and the operation of the facility over its lifetime, and it's all added up. It's discounted by the escalation of rates, and it's discounted back to a current, in my case, $2010. And from an economic, it's overly simplistic, but an economic perspective is if I have two choices and they both have the same net present value, then they're economically equivalent. If one has a higher net present value, then it is more expensive because I'm adding up all the costs. This would be like looking at a choice of a very expensive car. And so the bottom line is that we have those this model that is able to look at it. And I'm going to throw a statistic at here. What we're going to look at is quickly a probability statistic. This is a sample. This is the distribution of net present value. Since I have many variables that have uncertainties, wide ranges, the outcome tells you that it could fall within these ranges. These two have the same net present value, but you can see one is spread out much wider than the other. And what you're getting is an indication that this one here, whatever it is, has a greater uncertainty or risk associated. It could be very low, and it could be very high because of the uncertainties. And I'm going to quickly go through to give you some examples. We can accumulate the two and look at, as I said, the net present value. How much different from zero between the two is it? If it becomes more than, if it's a positive number the way that I set it up, nuclear is more costly. If it's less than a negative number, it is less expensive. So I want to look at simply the probability that it'll be positive or negative and what that likelihood is going to be. And just some of the analysis is this is a base case with no cap and trade of nuclear and coal. It's hard to tell what that means. This is the distribution of net present value. When I compare the two, I just overlaid the two. What you see is nuclear here and coal here. I'm sorry, combined cycle gas turbine here, nuclear here. Now there's no carbon tax. This area here is the only time that the two are about the same price. Combined cycle gas turbine is a lot less expensive under those conditions. If we were to look at that distribution, it's almost 99% of the time, given the uncertainties of everything else, capital cost, operating performance, and all the other factors, except for carbon tax, combined cycle. Now you put in not the full extent of a combined cycle or a carbon tax, but what is being legislated or proposed by various legislators, which is halted right now. There isn't anything happening. But the latest information, by just putting in that carbon tax, all of a sudden nuclear, which is the blue, is over here. Nuclear with a carbon tax becomes the preferred choice. And this is not the worst of what could happen to that industry. So we can see that the distribution, and now what we saw, which was a 99% of the time combined cycle, now 84% of the time nuclear is less expensive. That's a good bet if I had a carbon tax. If we went to the upper range of carbon, and I'll finish this up real quickly now, you can see that it becomes, well, if we, upper range of the nuclear capital, I increased it by 20%, the upper range, not the what we expect, but the upper range to reflect some of the things that we talked about and learned in Japan. It's a dead heat between nuclear and combined cycle, which means if we have the uncertainty of our concerns about carbon emissions and the uncertainty about the design of our nuclear plants, if you add both of those in, you're almost dead even in terms of economics. So the point is that, just to finish up here, is that there's a bunch of uncertainties. I only looked at two things: capital cost of the nuclear plant, which might be reflective of some of the things that the industry is facing because of the Japanese events, and then the impact of environmental concerns on combined cycle. So unfortunately, I left you with which one do you choose? And that's the industry's problem right now. We don't have a clear-cut answer. And depending on how you look at it, and that's why we probably want a portfolio, so that if we're going to make mistakes, we'll at least be spread out over a range of options. But thank you very much, and I look forward to your questions next. Anybody know how to get quick time into a PowerPoint presentation? Wasn't an option. That's been rubbed in my face. So if anybody has to take it.
Ben, I appreciate you inviting me here and the folks at Georgia Tech. I'm going to talk about something that I was very much a skeptic of, being a die-in-the-wool nuke in the past in my career. But fusion. Fusion is, for those out there that aren't of a scientific bent, it simply is combining, fusing together a couple atoms, usually hydrogen atoms. And what's neat about that is when you do that, there's a little bit, very little bit of mass loss. So what happens, this is Einstein in action, E equals mc squared. So you take that little bit of mass, square it, take times the speed of light and then square that, you got a lot of energy. So it's been the holy grail, if you will, for about 60 some years. The sun took about 50 million years to initiate fusion. So how long is it going to take here on Earth? There are endeavors underway, as many of you know, like the ITER project, which will be like 2028 now, it looks like, before they go operational. But back in 1960, the first laser was demonstrated. And then a fellow named John Knuckles proposed using laser energy for fusion energy. That was about the same time. That background there is Lawrence Livermore Lab, which used to be a Navy blimp base. Now, folks going after fusion, success with ignition. You have fusion, and ignition is when it burns by itself for a certain amount of time and creates all this heat, should be the culmination of this long journey between studying lasers and studying fusion energy. And so it looks like we're on the threshold. If we look at the number of experimental facilities, there have been about 6 up to this point, leading to the build of a national ignition facility out in Lawrence Livermore. Now, its sole intent is to accomplish ignition and then have further missions on stockpile stewardship. So this came out of a defense program, as many technologies do, as well as astrophysics and other type of sciences. Now, this has flown under the radar screen. I suspect many of you may not even have heard of the National Ignition Facility. It has now come to light, gained some notoriety and some controversy by those who are proponents of other types of fusion, like magnetic fusion. Now, in the National Ignition Facility there, it went operational in 2009. And it routinely, 1-2 times a day, achieves fusion. But the big trick is this ignition and burn, in which it is self-sustained to the point where there is a gain. In other words, more energy out than in. So it's fusion with gain that is the holy grail. Looking inside that building, we have here a target chamber, and that's where all the action happens. I'll explain that a little bit more in a minute. These other devices coming in are actually beam lines for the laser. That laser is 192 megajoules, which is the world's largest laser. The reflections are, stray light is the most powerful laser in the world. And so people said, when I started this project, it'd never be done. And then if you visit NIF, you'll see the 7 miracles, scientific miracles, technological challenges that were addressed to create this facility. All those little portholes around it are instrumentation, measuring time of flight of neutrons and X-rays, pictures of the shot. We call it the shot. And we shoot the laser at the target. In the center of that target, that target chamber, is the target. The target is about the size of an eraser. Obviously, this is magnified. Inside that target is a little sphere, about 2 millimeters in diameter, that contains the fuel, deuterium and tritium. So the trick is, the recipe is, put it in an oven, heat it up to hundreds of millions of degrees, and then create a pressure of hundreds of millions of atmospheres, and then you have fusion. Now the way that is achieved, and I'll show you a little video here, you'll see this thing, you hit by the laser. This is an oven. Right now it's made of gold. University of Rochester, the Omega site out there, laser has demonstrated that lead, cheap lead, even oxidized lead, is a better oven. When I say an oven, the laser hits this, heats it, X-rays are generated. The X-rays then hit this pellet, and the skin of the pellet is an ablator that blows off. And as it blows off, Newtonian physics, equal and opposite reaction, the fuel condenses from that couple millimeters to the size of a hair. And we get the high temperatures and pressures and fusion. So what it looks like going on inside that chamber hydrogen target, the layers, as I develop the story here, the laser is 4 slides, 2 sections. The laser is about 100 yards. 1990s technology for the light, laser inertial fusion energy, or engine. That laser is reduced to 30 feet. What makes that possible? Diodes. Okay. That's the difference between the 90s technology and what makes this a possibility. So in the design of the commercial application of this, diodes will play a big part. Another thing, earlier we looked at, there was Avalist, an earlier laser, and it operated 24/7 for a number of years. And availability is always a question, and maintainability. What we found out with those lasers is that they had line replaceable units, or designed line replaceable units, which means that you could pull out any of the components of that laser at any time without shutting it down because of some redundancy, and just replace them. This is all done automatically as it is now, robotically. So that was applied to the NIF design. Now, where do we stand on ignition? The expectation is 2012. Simply put, if you consider just a neutron generation, because this is just a neutron generating machine, ignition will be marked when 10 to the 19th neutrons are generated. Very energetic neutrons, 10 to the 14th MeV. Back in last December, we started up, we generated 10 to the 6th. Slow escalation now, we're currently at 5 times 10 to the 14th. About March, we're going to go to hopefully about 10 to the 16th. And that is the benchmark or the milestone for alpha burn, to begin alpha burn. Okay. And then onward to 10 to the 19th in 2012. So we're in new areas of science, digesting step by step as we go along. And as Undersecretary Coonan said, Office of Science, unless there's some physics we don't understand, we should be able to achieve ignition. So Secretary Chu said we shouldn't wait for ignition and start planning for the future, which is the commercial application of this technology. So, here's the road. 2009, facility was complete, 2012 ignition. We're looking at a market entry in the early 2020s of a probably 1 gigawatt plant. Now actually looking more towards a 1.5 gigawatt plant. Seems to be much more attractive, and that's what's being designed. And then fleet introductions and population in the 2030s. Now the call to action, I think everybody will recognize the different curves, need for carbon reduction, the energy demand that we're going to have. And the reality is that in the near future, we're all going to have to provide different technologies. Coal with CCS, renewables, natural gas, and fusion. We hope that fusion will eventually populate the world. Now, at some point, we've got to figure out what's attractive to the end users, which are the people, the NGOs, as Glenn mentioned, Stuart Brand and the Whole Earth Catalog, others. Well, we formed an advisory board, which I'm a member of. We're made up of CEOs, past CEOs, current CEOs, executives, and former executive regulators from the NRC. And so these were their things they wanted really to address. Okay. They had all come out, toured the facility, gone through the design presentations, looked at the conceptual, and said, hey, we're on board, but this is what has to be delivered. EPRI has been chartered by an ad hoc committee of utility executives to do a study of the different fusion technologies and look at who's going to be first to market. And hopefully we're going to come out okay on that. We also talked to the vendors. NIF was built at about $4.5 billion. Built over 10 years. And it won the International Project Management Award, even though it was a government facility, coming under time and below budget. The semiconductor industry, a number of vendors have done studies of the costing, the capacity, the industry capacity, optics industry, glass production readiness, manufacturing, there's a boiler tubes, construction. Parsons currently has been working on plant physical design. And manufacturing processes. Where we stand right now, assuming ignition in 2012, many vendors have assumed the risk after doing their due diligence of saying, okay, we want in, and we're negotiating joint ventures with the NSSS vendors. Large investors have come to the table and said, we want in before ignition because then there's going to be the rush. So that's where we are as far as commercialization. If there's any takeaway from this presentation, this is it. The primary source term disappears when the system is off. As that video demonstrated, it's over in the billionths of a second, couple billionths of a second. Right? It's hot. Can you misfire it? Yeah, you can shoot a pellet in there and it doesn't hit it. So what? Let the pellet. There's a means to do that. This is not a reactor. This is not a reactor. It doesn't make the definition of a reactor. It doesn't cut it. It is an engine. It is very similar, analogous to your car engine. For this thing to operate as a baseload facility, 600 cycles per second. That's how fast those pellets have to go in. And I know that's going to generate some questions. But it is not a reactor. There is no continuous nuclear reaction. So, runaway reaction is not possible. Low residual decay heat, not from fuel, just some activation products. Off normal conditions, design-based accident, lithium fire, you'll walk away from it. No consequences on the site boundary. Let the place burn down beyond design-based accident. So there's no need for safety class components. The other thing, the plant itself, the new plant, commercial application, will be smaller than a fossil fuel, and some of the CEOs are asking now, or studying, whether they can replace the fossil plants in their urban areas. Okay, so that's pretty much the story of life that I suspect you're going to hear about quite a bit in the news in the forthcoming year. Again, this will hit the market. It's designed, its trains left the station early 2020s. Market penetration. There are no safety systems, no safety consequences. Off-site, there is no long-term storage requirement for radioactive waste. The waste that is generated is low level. So that's pretty much the story on life. That is 1.5 gigawatts. It is economical from 400 megawatts to 1.5. However, this beast likes to run big. And at 1.5 gigawatts, cost of electricity is around $40 to $50 per megawatt hour. So, I'm sorry, the NIF is located in Lawrence Livermore National Lab. If you want to find it in that and life on the internet, just Google NIF, N-I-F, and it'll come up. You know, Tom Friedman was out there, you know, New York Times science writer, and he called this thing the holy cow, the real holy cow game changer. So, and National Geographic, BBC, and whatnot have been out there recently doing specials. Ben, thank you.
At this point, let's have break into a Q&A session for about for the time remaining. So if the speakers would have a seat there. Dorothy, I'll give you a microphone if you would.
As you can see, I'm excited. This is about 50 days of fuel right here at 1.5 megawatts.
I bet there are a few questions.
With regard to the cost of nuclear reactors, And, you know, we're hearing the latest popular press, certainly in Georgia, is talking about $6,500 a kilowatt all-in price for Vogtle. Some WAGs expect it to go to 8,000 when it's all finished. What's the outlook for getting these prices down? What can be done? Is it a function of the custom-built situation still, or what can we do over the next generation to get the cost of these units down?
I can try to address that. The cost is incredibly high. One thing, the capital cost basically is all up front with the nuclear plant. The fuel is actually a minimal cost. It's the lowest cost of everything rolled into it. But getting the capital costs down, I think if we start building more plants, it's like anything else. If you start, you know, getting the vendors where they're working on more than onesie, twosie plants, I think you could get the price down somewhat, 10 to 20% just from that. There are other savings methods that could be done depending on the cost of review. We have the combined operating license procedures now in place, so you don't have to get a license to build it and then wait for everybody to come and have a hearing and then see if you can actually, after you paid your $5 billion, see if you can operate it, which is how we used to do it, and it was a bit crazy to do it that way. Now the construction operating license process is done in one shot, and it's done all at once. So you get you basically get your operating license when you get the construction license. We actually haven't built any with that procedure yet, so everything is still in a forecast mode, and a lot of things as folks pointed out, there's a big variance on many of these things. So they're trying to be risk averse in their estimates. I think if we start building them, we start building more than one or two at a time, you will see the cost come back to around probably around 4 to 5 billion per unit. But these are very large units. We're talking, you know, 1,500 megawatt units. So they're going to supply. It's the equivalent of 1,500 wind machines operating constantly. So yeah, you have to put it in perspective with what you're getting. You're also getting a plant that's going to run around probably 80 to 100 years. You can get them to last that long. And that's why we're seeing all the life extensions. We keep over-engineering these things, and that's why the life is extended. So you get the value out the other end, but the capital cost is pretty high.
Yeah, I have a question with regard to the waste. Okay, so the zirconia has this steam reaction, but it also has a band gap of 5.5 volts. And so there's a non-thermal radiolytic process that makes hydrogen. So I'm wondering how effective is this convection cooling going to be for the non-thermal process?
That's a good question. There's a lot of water chemistry that goes into nuclear plants and in controlling corrosion and other things with regard to spent fuel ponds. The zirconium and zircaloy alloy is mainly selected because of its neutronic properties and ability to contain fission gas and have the primary barrier for fission product release, to avoid fission product release. But a lot of technology went into the fuel. It's fairly pretty stout, the light water reactor technology for the fuel. As long as you don't run it up to 2,200 degrees, you're in good shape, which none of the plants are designed to run it that hot. Which calls into question another aspect. If we're going to use nuclear power, you've talked about hydrogen production and the fact that we're going to all have hydrogen-powered cars in 20 years, and it sounds great, except that the hydrogen production requires 1,000-degree temperatures and higher to efficiently produce that. You can't achieve that with current light water reactor technology. So we have to go with new reactor technology to be able to produce that hydrogen to run our transportation sector. So that puts the emphasis, DOE has recognized this, and they've put emphasis on molten salt research, because you can have molten salt reactors that can operate at those very high temperatures, and there's no problem because the salt is molten. It basically is not going to have a boil-off problem.
Yes, thank you. Is it Dr. Debs?
No, it's
Right. Mr. Niff, Mr. You did talk about there being low-level radioactive waste, and I wondered if you could comment on the type of waste and the amount of waste, and also I was concerned about, I wanted to thank you for coming down, and also say, actually the Vogel was supposed to be 600 million for 4, and it was over, I think, 8.3 billion, and the largest ratepayer increase. What? Oh, for 2.
I
We
remember
ended
I
up
was
with
with
2.
the commission when it was licensed.
Oh, you were? Okay. And I did have a concern about the talk about reprocessing. I'd like to hear more about it because I'd like to know, is the information that you are sharing with us about reprocessing coming from Areva, the French company, and is there an association of Areva either directly with you or with Georgia Tech Institute? Thank you.
I was just a consultant for EDF for a month. EDF, Electricity de France. Areva is an independent company from EDF. EDF is the electric utility. Basically, I'm referring to our reprocessing operations in Japan, France, the UK, just about anywhere, China. Everyone has reprocessing except the United States right now. You're talking about defense waste, and yeah, and commercial waste can be packaged and gotten down to extremely low volumes. You're talking about waste calcining operations have to occur for that to happen. But if you're going to take it and just make plutonium, which was done in the United States, that's what results in these large tank farms that have not been handled because all they did was reprocess the fuel and not manage the waste products from that. Their goal was to produce plutonium. And if that's your goal and you don't worry about what else to do with the volumes of high-level waste that result because the plutonium is only less than a fraction of a percent of the total fuel volume that you're recovering, the rest has gone into the waste volume. If you don't handle that, then you have these very large tanks. But if you go to a fully closed nuclear fuel cycle for the power cycle, and you handle these basic waste streams that are basically, you have to recycle all that stuff, you have to calcine the waste, it gets down to extremely low volumes. 95% of what is taken out of the reactor goes back in the reactor. Areva has proposed a pilot plant to the United States government, and that's being discussed, and they believe that they can actually run it at a profit, or they wouldn't be proposing it. They reprocess 85% of their power fuel at this time. So 15% is not reprocessed, and most of it's sitting in their waste ponds because they let it decay.
Yes. I'll make it quick. The low-level waste, iron 59, some short-lived, some long-lived isotopes, but all above ground. They're not the category 2 type waste. The preponderance of waste is comparable for this facility currently as a light water reactor. The reason is that target chamber I showed is not stainless, but it is steel, is tungsten steel. And so one of the premises of this design, the commercial design, is no new materials, no exotics, no new technologies. So using tungsten steel, every 2 years it takes an outage to automatically replace that. So that's a chunk of metal there. Now, once silicon carbide and the future, exotic metals are qualified, then that goes away completely. But initially, that's a major contributor.
Howard, I appreciate your presentation. given the economics and the between nuclear and combined cycle gas turbines, and what I see is a minimum possibility of a carbon tax being politically acceptable over the next near future, anyway, 5-10 years maybe. I'd appreciate your perspective on the chances of an additional nuclear plant, or how many of them will be built over the next 5 or 10 years, or started over the next 5 or 10 years, in addition to our Vogtle plant.
Well, it's an excellent question. Well, a couple things. One is, you have to, I don't know where this audience sits on nuclear power, but in terms of this country's moving forward with alternative energy and not dependent on hostile nations to supply us with energy, it took a lot of guts for Southern Company, along with Oglethorpe and MEAG, to go forward with economic, financial. Shoreham, if you look at the economics, put Long Island Lighting Company into bankruptcy. Now the events occurred where things happen, like if you're old enough to remember when credit cards were, or actually you can get a CD for 14% or something like that. Or your credit cards were 20-some%. Well, that utility was spending 18% on their interest charges. So when you had a $4 or $5 billion debt that's sitting there, non-generating revenues. But anyhow, I don't think many. The reason we're getting Vogtle 3 and 4, you're getting over SCANA is looking. They got an application in as well for the Cooper nuclear plant. Is it Cooper? I think, if you recall, under the Energy Policy Act, there was certain financial gains, substantial incentives to be the first 4, 5, or 6 nuclear plants. So investment tax credits, guarantees on financing, and so forth, which made it very palatable to build those. I personally, aside from the fact that I think it's a great technology for us, that doesn't produce the carbon emissions that we're concerned about, I wouldn't recommend it to one of my clients. That I think during the interim, combined cycle is the way to go. I have a far greater amount of flexibility. I can build it modularly. I can start it out as peakers and then add on the combined cycle aspect. It might cost me something for that, but it surely does provide me with the financial flexibility, and given gas prices, at a cheaper price. So bottom line is, right now it's a slam dunk.
We have time for one more question.
Mr. Jadine, I heard a lot of. I have sort of a question for you, Mr. Axelrod. You talk about long-term needs, and I agree with you that spent fuel reprocessing and storage is a problem. The thing that I didn't hear you talking about was water consumption and evaporative loss. And I was, you can see spent fuel, and I think that gets people's attention, but there's a lot less public awareness about water consumption. And you take a plant like Vogtle, you can read the EIS, and there's 40 to 45 million gallons per day between 2 units, and that will double with the expansion. How close are we to implementing technologies that are going to reduce the amount of evaporative loss, water consumption, implementing cooling technologies that are going to be able to scale that back? And how important is that to the industry right now? How much are you advising your clients? And then, Mr. Axelrod in particular, how much in your economic analysis have you considered environmental regime change in the same way that there has been proposed a carbon tax? What if there's been grumblings in the environmental community that EPA would like to monitor water withdrawals? How do you feel how do you value that going forward if they were to do so under the Clean Water Act and make that argument?
I'll take a shot at it. Water is a resource that's very important, and you need a certain amount of water and reserve water and cooling water or other things to operate a plant. You got a large heat sink because the efficiency is around 30-ish%. If you go to molten salt design, you got an efficiency of around 60%. So it's really, we've had nuclear plants that use gray water cooling from sewage in markets where the water is more costly. So it's really what you want to adapt the plant to do. Part of the reason they chose that site was the availability of that water to be able to service those plants. But it's really a matter of cost and benefit and where you're going to get your water. But yeah, you have to have the resource.
Can I add something to that? The talking about this life design, one of the options, and this was brought out last month in the Southern States Energy Board annual meeting, that the cooling towers there you saw were forced convection. They also have a dry application to them. So run without water and adds about $2 to $3 per megawatt hour. It comes with a cost, but it has that capability.
All down to money.
Yeah. But
Well, let me just, I think you implied it on combined cycle. One is the scale is quite different. It's not going to be 1,500 megawatts. They tend to be 300, 400, or 500 megawatts. They are closer to urban centers. Also, they're able to use closed cycle cooling systems. They're highly efficient. They're among the most efficient in terms of fuel cycle. So I'm not an expert on how much water from one to the other, but it doesn't usually rise to a level of public discussion as to the water usage relative to nuclear plants. So I'm kind of guessing that it's not as major of an issue, relatively speaking, but some might argue with me. And
Let's thank you all very much for attending and your questions, and let's please thank our distinguished speakers for their participation. Look for a few announcements in December about the January 25th program. Look forward to seeing you then. Thank you for being here.